So we look at nuclear energy, and there is no way to talk about nuclear energy without leaving out the great Albert Einstein. This equation was responsible for what we know today as the atomic bomb. This equation showed the relationship between energy and mass. So what Einstein was able to discover was that during a basic reaction between reactants forming products, that change in mass that occurs from reactants to products, that change in mass results in energy. He was able to work it out. So here's what we have. We have here that the energy is equal to the change in mass called the mass defect by the speed of light squared. So this was known as the energy-mass relationship. How do we find, well, we all know C. C is the speed of light, and the speed of light is what? Alright, 3 by 10 to the power of 8. Remember that? 3 by 10 to the power of 8 meters per second. Right? So we have the speed of light, and we have to find our mass defect. What is mass defect? Mass defect is the difference in mass of the reactants and the product. It's always very, very small change in mass during a reaction. So all we need to do to find the energy in any reaction is find the mass of the reactants, minus it from the mass, minus the mass of the products from it, and then multiply it by the speed of light squared. Very simple. But the problem with these calculations are these calculations have very, very small values. So the values of mass are like in the minus 27 30s. So what they do is they write something called the atomic mass. And the atomic mass, which is 1U, is equal to 1. Look at have it in the example, 1.6605 by 10 to the minus 27 kilograms. So because the values are very small, we use a new unit called the atomic mass. Okay? So how do we find the energy for a reaction? Let's take a look at this example here. Well, if we look at this example, this reaction is a hydrogen atom reacting with a neutron. Hydrogen with a neutron gives you this atom plus gamma radiation. Okay? So these are the masses in atomic mass of the hydrogen, of the isotope of hydrogen. And now what's an isotope? Same atomic number but different mass number. So this is an isotope of hydrogen, a neutron, and this is the conversion. And the question is, how much energy is released in this reaction? So we all know, say a reaction, what we need to use is E is equal to mc squared. So the first thing we need to do is to find mass defect. To find mass defect is the mass of the reactants minus mass of the products. So the reactants are what? A hydrogen atom, 1.007825, plus a neutron, 1.008665, minus the mass of the product, which is only this is gamma, right? Gamma has no mass, is a ray, and a helium, isotope of hydrogen, 2.014012. Try to do this all at once in a calculator, right? The value that you should get when you work this out is 0.002388U. Problem is, we need to find everything in its correct SI unit, so we must convert. So we multiply by 1.6605 by 10 to the minus 27, which will give us a value of, try to be exact as possible because the energies are very, very small, 3.96527 by 10 to the minus 30 kilograms. There is no need to write this down really because you could go from this step to this step in the calculator straight to get the answer. So therefore, the change in E is equal to mc squared, which is this value here, 3.96527 by 10 to the minus 30 by 3 by 10 to the 8 squared. The number one mistakes, y'all, in doing these questions is forgetting to square this. Okay? Please remember to square it. And as I always tell my students, there's a value that is always around the minus 11, 12, 13 range. So when you work this out, the answer that you should get is 3.57 by 10 to the minus 13 joules. Right? Let's look at it quickly. Balance the equation, because some questions may ask you to balance it first. Make sure balance 1 plus 1 is 2, 1 plus 0 is 1. Good. Find the change in mass, mass of reactants minus mass of products, right? Find it in, you'll get it in U, multiply it by the conversion to get in kilograms, then multiply it by the speed of light squared. Please don't forget to do this. And when you work it out, you get this answer. If you get something positive 30, big values, that definitely you know you're wrong. So therefore, look for the range minus 11, minus 12, minus 13. That's generally what we work with. Okay? So that's it for nuclear energy. There are two types of reactions that we look at. We look at nuclear fusion and nuclear fission. Fusion is where you have two small particles joining to form one, like in the sun, right? Like what the reactions are going in the sun. Or fission is where you have one big particle splitting to give you two small particles, right? So you have fusion and fission. You also need to know about radioisotopes, their uses. One of the uses is tracers, treating cancer, carbon dating. So all these things you all should read up on. And that basically takes us to the end of nuclear physics. Okay? So thanks a lot. And I hope this benefits you.